This is a help video for the DC Operational Amplifiers game in Circuit Tutor, Level 3, Problem Type 1. So we'll go ahead and go into that game. And of course, as always, we recommend that you certainly go through the introductory tutorial carefully prior to playing the game so that you will be prepared with the basic theory involved in these problems. It's also a great idea to look at examples at the appropriate level before you begin to solve problems. That will oftentimes actually save you a lot of time in trying to figure out how to do them by watching some examples first. Okay, so I'm going to go ahead and go straight into a problem here at level 3. Okay, so we have a problem here with one op amp. And we have the instructions also, just the general instructions, which you can always access from the help button up here if you need those. We see that there are actually 3 different inputs here. This is going to be called a summing amplifier type of circuit, and we'll discuss the function of that a little bit later. It uses a single op amp, and you can see that basically it's forming, in a sense, a type of average of these 3 inputs, which even have different polarities through different resistors, and that input here then goes into basically a non-inverting amplifier configuration that will give us the output voltage. So that's basically what's going to happen, but we're going to go ahead and just analyze this very straightforwardly using nodal analysis, which is essentially always used for op-amp circuits because of the fact that they may not be planar, and also some of the circuitry is really hidden inside the amplifier itself. So just to review, we know that the input impedance of the amplifier is very, very high, virtually infinite, so no current goes into the positive terminal or into the negative terminal. That'll be one of the basic ideas that we use in solving the circuit. And also because this output is connected effectively to a voltage-controlled voltage source with essentially infinite gain, that gain will basically feed back through the feedback resistor and force these 2 input voltages to be essentially the same. So we have what's called a virtual short here, even though no current actually goes from the positive to the negative. But they will have the same voltage, which is an unusual type of situation that's permitted using an operational amplifier. Okay, so let's go ahead and solve this using nodal analysis, keeping in mind the guidelines I just stated. So since we have a voltage source and we are going to do nodal analysis, we have to do voltage constraint equations. In fact, we have 3 voltage sources, so we will need one for each of those sources. And it's advising us here that there's 2 sources with the same value, so it'll highlight it when we select the appropriate radio button up here. So let's select the 2 volt source first, which is the bottom one here. And it highlights this so we know that. And that basically fixes the value of V1. And it fixes it at a certain value, so we'll put in that term there. So V1 basically is going to be given by negative 2 volts here because of the polarity of that source. Or in other words, 0 minus V1 equals 2, and that's equivalent to this. So we'll check that equation. And now we'll do a similar thing for the middle 6 volt source here. Select that, and right now it's V5 equals a fixed value. So we'll put in the 5 there, and that's again going to be negative, and in this case a negative 6 volts. So we'll check that. And finally the other 2 volt source on the top here, select that, and now we have V6 is going to be equal to a fixed voltage there, determined by that source. And just a reminder that all of these ground symbols are basically connected together, just the wire isn't shown, but you can imagine a wire going all the way here and over to here, and it's also connected to the power supplies for the op amp, which are not shown either, the positive and negative supplies that the op amp always has. Okay, so V6 will be given by plus 2 volts because of the polarity of that op amp, so it just basically says V6 minus 0 is 2. So that is correct. And now we have the special type of equation that we always have for op amps, which basically expresses the fact that these 2 inputs are kept by the feedback at the same voltage. So that's called an op amp input constraint equation. And we could write it various ways, but it basically says V2 equals V3 So we could write V3 minus V2 is 0, or I'll just write V3 equals V2, I guess. Doesn't really matter how we write it. But we don't know either value, we just know that they have to be the same. Okay, so that is correct, and now we have to do sort of the central equations in any nodal analysis, which are Kirchhoff's current law equations, expressing the fact that the sum of the currents entering any closed surface or leaving any closed surface has to be 0 in a circuit. And the surface can enclose a node or could even be a supernode in some cases. So here, if we look at node 1, for example, we cannot write a KCL equation there because it's connected to a voltage source. And that means we don't know the current through a voltage source, we only know its voltage. Therefore, there's no way to write that equation. And similarly for V5 or V6, all the same problem. So none of those can be written. So then if we look at V2, well, that's connected only to resistors. And then this connection to the input of the op amp, remember how much current goes there? So the answer is 0, because this has infinite input impedance in the ideal case. And even practically, it's very, very high. So because that's 0, we can easily write that. So we will do so for V2, and we need to do so. And basically, we need to add the 3 currents leaving V2, which go through the 8 ohm, the 3 ohm, and the other 3 ohm. So those are all differences of node voltages. So we'll use 3 of these terms, and that sums to 0 here. So in each case, we'll go from V2 to the other node. So V2 minus V1 over 3, that's the current through the 3 ohm here. Then V2 minus V5 over 3 is the current through this 3 ohm. And finally, V2 minus V6, V6 over 8 ohms. And notice I'm using the tab key on the keyboard to go easily between these different boxes, which can speed it up a lot on the data entry here. Okay, so we'll check that equation now. And that is correct. And now if we continue looking at nodes, we've dealt with these. So we can think about node 4 perhaps. So think for a moment, can we write a KCL equation for node 4? So in light of what I said earlier, the answer is a resounding no. We cannot do that because remember that I said the output of the op amp is effectively connected to the output of a voltage-controlled voltage source. Therefore, we don't know the current through that source. In other words, we don't know the current coming out of the op amp. That's something we're going to find, but we don't know it now. And or we could find it anyway. And so we cannot write a KCL equation for node 4. However, if we go to node 3, the last remaining node, we can do it there because, again, the current through the negative input, hopefully you remember by now, that current is 0. There is no current there. So these currents are only involved resistors, so that we can write. So we'll select node 3. And each of those, well, one of them is going to be a difference of node voltages through the 2 ohm, and then this one is going to ground. So we just have one node voltage divided by resistance, and that's equal to 0. So these are just Ohm's law type of terms. So first we'll fill in the one going through the 2 ohm to the right there, leaving that node 3. So that would be V3 minus V4 divided by the 2 ohms, just again based on simple Ohm's law using passive sign convention. I'm always trying to do it using passive sign convention so I don't have to put a minus sign in Ohm's law. At least for V3, it's passive, it's active for V4. And then the next one would be V3 minus 0, or just V3 divided by 7 ohms. I'm sorry, 7, which is the current going down through the 7 ohm resistor. So we'll check that. And that is indeed correct. So now we can maybe take stock of what we've done here. We have 1, 2, 3, 4, 5, 6 unknowns here, 6 node voltages we're dealing with. And we have 1, 2, 3, 4, 5, 6 equations, so we are done here. We do, however, have to write equations for the SOT variables, which we have 2. So one of them is a SOT current, so we'll select SOT branch current. So I0 is going through the 2 volt source. Now that's very difficult to find normally, but in this case it's in series with an 8 ohm resistor, so we can use Ohm's law for that resistor to actually find it rather easily. So we'll say I naught equals, and then that'll be, using Ohm's law for the resistor, that'll be V6 minus V2, since we want the current going to the right in the direction of I naught, divided by the 8 ohms. Okay, so that'll give us that current. And we'll check that. And then our other SOT variable is V40, which is using the double subscript notation, just means V4 minus V0, which is the ground potential. And so we'll select a SOT non-branch voltage there because that does not appear across any one circuit element. And so that's very simple. It's just V4 minus 0. We don't have to include the minus 0, of course, so we just put in V4, and that's done. Okay, so now we have all the equations we need. We'll click No More Equations. And now it advises us that we need to put these into simplified form on standard form that we use for that. So we'll begin here. We have a total of 6 equations to enter, so it'll take a little bit, but they're not too complicated. So V1 is just equal to -2, so we'll make a coefficient of 1 there for V1, and then a constant term of -2 here. And I could use the tab key, but here it's probably faster to just click. And then V5 is -6, so our next equation, we'll just put a 1 coefficient of V5, and then this will be -6 is the constant term. And then the third equation says V6 is 2, so that will be a 1 here, and then this will be a 2. And finally, well, not finally, but next one is V3 equals V2, so we could just maybe put a 1 here and a -1 here will work, and that's equal to 0. Just expresses the fact that V2 and V3 are the same. And then this equation will be our, oops, I'm sorry, I put that in the wrong row there. That should have gone a row below because we already used that slot. So I meant to put that down here. We'll put zeros back up there where they belong. Yeah, that was just the equation V3 equals V. No, this is the equation V3 equals V2, and this was one V6 equals to 2, so that's still there. Good. Okay, so now we're down in the 5th row, and here for V1 we have basically just this term, so it's -1/3, and I can type that as a fraction if I like, so -1/3, or you can just put in the decimal -0.33, -0.3333. The V2 here has 1/3 plus 1/3 plus 1/8. So I've just kind of done that on paper over here and putting it in the calculator is 0.7917. That's for the V2 coefficient. And then there's no V3 or V4, but we have a V5, which is -1/3 in this equation. So that'll be -1/3. I'll just put it in as a fraction. And then V6 has just this term, which is -1/8. And then that's all still equal to 0. So that's that equation. And then the last one is a little bit simpler. So we have 1/2 plus 1/7. So as done over here, that's 0.6429, just using calculator. And so that's the coefficient of V3. And then we have V4 is -1/2, basically. So -1/2, or -0.5. And so now we should have entered all those correctly. So we'll check that. Probably would have been a good idea to proofread. And by the way, we could have just skipped all this and gone to the final answer entry if you know what the final answer is or how to figure that out quickly. And that might be possible in this circuit, as I'll discuss at the end. But in any case, I'm just showing you the full solution. Okay, so now that's printed on the screen, and it wants us to put that into matrix form, although we probably won't really use this form, but we'll just copy it and click the button, and that's done. Very easy. And now it just advises not a good idea to use MATLAB or calculators to solve this matrix equation. Instead, probably easier just to do it by hand, just using conventional methods, because that'll really be more like what you do on a test, for example. So first of all, V1, we just know that one is -2 from this equation. V5 is -6, so we'll just put that in. V6 is 2, so we'll put that in. And now we also know that V3 and V2 are the same, but we don't know either of those yet, so we'll have to hold off on those. So now we have to use the more complicated equations, namely these two bottom ones that we haven't used yet. And so I've just copied the fifth line here over and substituted in. So we have minus 0.3333 times V1, which remember that's -2, so we just put that in there, plus the 0.7917 V2, minus the 0.3333, or a third of V5, and remember we know V5 is -6 here, so I just put in the -6, and finally minus 1/8 times V6, which is just 2. So put that in here, and now we just have one unknown there. It's actually a very easy problem, so we can just collect all the constants, multiply this out, and this, move them all to the right hand side, and that gives us basically -2/3 minus 2 from this term, and then plus 1/4 from this term, and then just adding that up, that's on a calculator, that's -2.417, dividing by this coefficient then just gives us the answer, which is -3.053. And do remember that V2 and V3 are the same, so we can enter that for both of those values and kill two birds with one stone here. So V2 is -3.053. And I'll just, get the whole thing there, copy it and paste it there. And then using the last equation, now we can find V4. So we have the 0.6429 V3, and we just found the V3. It's -3.053. Plug that in there, and that's equal to just moving this term over to the other side. That's going to be 0.5 V4, and we want V4, so we'll just divide both sides by 1/2 and just do the arithmetic there, and that gives us -3.925. So that's our V4. 3.925, and that should hopefully be correct, so we'll check that. And again, we could skip this step if we know how to get the final answer, but I'll just do it all here. And that's been printed on the bottom of the screen here. We have to scroll down, and then we need to find the SOT variables. So here I've just written that out. So I naught is V6 minus V2 over 8 ohms, and I just plugged in the values we just found, which are actually printed down here at the bottom of the screen. So V6 is 2 volts, and minus V2 is going to be plus 3.053 from this, and then we just divide by the 8 ohms, and that works out to be 0.6316 amperes. And then the V40, that's just equal to V4, which we already found, so that's the -3.925. Oh, I'm sorry. No, I don't want to give up at all. Click the wrong button. I want the check answers button. Yeah, I wouldn't not want to give up at this stage. Okay, and that's done. And basically now it's making a transcript, PDF transcript, as it always does. And it does offer the option to view a detailed explanation of the complete solution, so I'll just show that just for completeness here. And it'll highlight each KCL equation in turn and show how it was derived. Just fairly straightforward here, but in case if you have any questions, you can review that. I won't go through all of this now, but we'll just close it up. And then you can review work here. Click that button to view your PDF transcripts of all your work, including both correct and incorrect steps. That completes this. Oh, actually, there's one more thing I wanted to do before completing that problem. So I did want to discuss sort of the idea of this problem. We basically had 3 input voltages connected to a common point, which was the positive input of the op amp, through, I'm going to call them conductances because that makes it easy, G1, G2, and G3. And what is this circuit really? Well, if we just apply KCL at this node, very easily using Ohm's law, which is I equals, say, V1 G1 plus V2 G2 plus V3 G3, that has to be, well, I'm sorry, it's G1 times V1 minus V plus G2 times V2 minus V plus G3 times V3 minus V plus. Anyway, you can solve all that for V plus, and it gives you this formula. So what we see is that the V plus, the input on the positive terminal of the op amp, is just really a weighted average of those three different input voltages, weighted according to their respective conductances. And if you made them all equal, which is commonly done, then this would all cancel out. We just have a factor of 3 in the denominator, because they'd all be the same G. And so there you'd be getting basically the arithmetic average of those three voltages. Now, this is a weighted average in this circuit, and so it doesn't give you just a simple average, but that might be useful also. So that's really the purpose of this circuit, is what we call a summary circuit, as discussed in the introductory tutorial. Okay, so that completes this problem.